analysis. In this lesson, we will continue with power flow solution for large power systems. We will first make use of rectangular coordinate formulation for Newton-Raphson load flow, and we will see how this helps in speeding up the algorithm. Then we will talk about how to model regulating transformers in power flow formulation, and finally we will talk about applications of power flow in power systems. Well, on completion of this lesson, you should be able to develop a faster Newton-Raphson algorithm for power flow. You should be able to develop regulating transformer models for in power flow problem and explain the application areas of power flow solution in power systems. So, as we discussed in the last lesson, that Gauss-Seidel algorithm, though is the simplest and requires minimum time per iteration, the number of iterations is dependent on the system size and therefore increases with system size. Because of this, the total time taken for the Gauss-Seidel algorithm for large systems becomes much more than the Newton-Raphson or the fast decouple algorithms, and therefore this is generally not preferred over the other two algorithms, that is Newton-Raphson and fast decouple algorithms. Now, in Newton-Raphson algorithm, we had developed the algorithm for the polar coordinate version, that is, we have used the polar coordinate version of voltage as voltage magnitude and angle delta, because this has certain advantage. Polar version using V and delta of Newton-Raphson power flow is computationally more efficient than rectangular version, which uses voltage as voltage phasor as E plus JF, that is in rectangular coordinate formulation, because in this case the voltage equations for, in case of polar version, the voltage equations for PV buses are not required, whereas in case of rectangular version, the voltage magnitude equation V square is equal to E plus JF square is required for each PV bus. That is, in case of the polar version, when we are formulating the Newton-Raphson algorithm, the voltage magnitude at the PV buses are already known, so we do not need to find those values, and therefore those equations are not required and not formulated in the polar coordinate version of the Newton-Raphson power flow algorithm. But if we use the rectangular version, that is, if we write the voltage as E plus JF, voltage phasor as E plus JF, then since we know at PV buses the voltage magnitude, so we will have to write an equation for this as V square is equal to E plus JF whole square. So this equation has to be included in the rectangular coordinate version of the Newton-Raphson load flow for each PV bus. That is, the total number of equations in this case will be equal to 2 into n minus 1, where n is the number of buses in the power system in case of rectangular coordinates, where in case of polar version the number of equations will be reduced by the number of PV buses present. So this increases the size of the Jacobian matrix, and therefore the solution time is expected to be higher. However, even if we are using the polar version, we can take advantage of rectangular coordinate version, in the sense that in case of polar coordinate version, we have to calculate the trigonometric functions, that is cos and sine terms, for the Jacobian matrix elements calculation. Instead of using these trigonometric functions, if we calculate the elements of the Jacobian matrix using the rectangular version of the voltage, then we will be able to avoid the calculation of trigonometric functions, and this speeds up the solution somewhat. So, if we look at this in rectangular coordinate version, if we write, then for m not equal to I, that is for off diagonal elements, HIM is equal to LIM. These are the matrix Jacobian matrix submatrices of the Jacobian. This is equal to AM Fi minus BM EI, and NIM is equal to minus NIM, sorry, this should be LIM, it should not be J, and LIM is equal to AM EI plus BM Fi. Similarly, the diagonal elements can also be computed as shown here, as HII is equal to minus QI minus BII VI magnitude square, NII is equal to PI plus GII VI square, and this should be LII is equal to PI minus GII VI square. Sorry, this is M, and this is LII is equal to QI minus BII VI square, where YIM, that is the imth element of the admittance matrix, is written as GIM plus JBIM. That is, this is the conductance part and this is the susceptance part, and voltage phasor is written in rectangular coordinate, VI is equal to EI plus JFI, and therefore, if we use this, then we get AM plus JBM is equal to GIM plus JBIM into EM plus JFM. So, this multiplication of Y with V is put here as A plus JB. So, if we use this, then as we have seen, we can compute all the elements of the Jacobian matrix in terms of A, M, F, B, M, EI and so on. That is, we do not need to compute the trigonometric functions cos, sine terms in this case, and this does improve the computational speed of the algorithm to some extent. Next, we will talk about including regulating transformers in power flow solution. Now, what are regulating transformers? Regulating transformers are basically transformers which are used to control the voltage magnitude or the power flow on the transmission line. So, voltage magnitude of the bus bar or the power flow through a transmission line. In fact, in AC system, it is very difficult to control the power flow, real power flow on the transmission line, because it is dictated by the voltage phasors at different buses and the admittance of the transmission lines. Of course, with power electronics devices coming up in recent years, now we have what we call devices which can control the power flow on the transmission lines. These devices are called flexible AC transmission systems or FACTS devices. So, these devices can change the voltage phasor angle across the line and therefore change the power flow on the transmission line. This is same as trying to use a phase shifting transformer. Similarly, we can change the magnitude of the voltage at the bus bar by a small amount, and thereby we can control the reactive power flow in the transmission line and control the voltage at the bus bars. So, these are done by means of regulating transformers or fax devices. Of course, including fax devices in power flow is somewhat complicated and will not be done in this course. We will be trying to use the modeling of regulating transformers, which serve similar kind of purpose. So, we have basically two kinds of regulating transformers, one which changes the voltage magnitude by a small amount, that is, you can have what we call tap changing transformers, or sometimes we call them that these transformers tap can be changed offline or online. If it is online, then we say online tap changing transformer, OLTC, or if we have offline, then we call them as offline tap changing transformers. So, what we are trying to do is, a transformer has a nominal turns ratio. That is, if suppose it is a 33 kV to 11 kV transformer, then at the nominal tap position, if we have the 33 kV side voltage at 33 kV, then 11 kV side voltage will be 11 kV. Now, if we change the tap on the winding on the high voltage side, if we make it the number of turns larger than what it was, then what happens? The high voltage side voltage remains 33, but the number of turns are increased. So, the turns ratio now is larger, and therefore, on the 11 kV side the voltage will be lower. Similarly, if we reduce the number of turns by putting the tap below the nominal value, then the voltage on the 11 kV side will increase. In this way, by changing the taps, we can change the voltage at the other end of the transformer or other side of the transformer. So, regulating transformers job is to provide small components of voltage, typically of the order of plus minus 10% to the line or phase voltage. This is what they do. Now, we will see how this is done. This is a regulating transformer for voltage control, that is for changing the voltage. What we are doing here is, we are adding this delta VAN to the voltage VAN, which is there. Say this is your AN VAN. Here, using this transformer, we are adding some voltage to this here, and therefore, the voltage output at this point is VAN plus delta VAN. Same case will be here, VBN plus delta VBN and VCN plus delta VCN at this point. That means, the voltage at these terminals are higher than what they were earlier, because using this regulating transformer, we are adding the voltage in phase with the voltage which was already there at the terminal of the this line. So, here this way we can add, similarly we can subtract the voltage also, and thereby reduce the voltage at the terminal here. So, this is what is done by the regulating transformer for voltage control. Similarly, instead of having a voltage control, if we want to have control over the power flow on the transmission line, then what do we need? We have already seen that the real power flow on the transmission line is dependent on the phase angle at the two ends of the line. That is, it is dependent on delta I minus delta j. Now, if we want to increase the power flow on this line from I to j, then delta I minus delta j must be increased. Now, we can do this by increasing the angle delta I by a small amount. This can be done by means of a phase shifting transformer. Here if we see, this is a phase shifting transformer. Now, this is the normal transformer, which is a delta connected one here. Here the terminal voltage is A. So, the voltage from the fictitious neutral, if you see, is VAN. Similarly, here the voltage is B, VAN is the voltage that we get, and here the voltage is C. So, VCN is the voltage. Now, what we are doing is we are adding or subtracting a voltage which is normal to the phase voltage. So, if we see at this point, VAN will be like this, and we are either adding voltage delta VAN in this direction, which is 90 degrees to VAN, or in this direction again, which is 90 degrees to VAN. So, if we do it in this direction, it is going to reduce the angle. If we are going to use it in this direction, it is going to increase the angle. Now, these points which are there, that is adding the voltage or reducing the voltage in all the three phases, they are ganged, means they move together. So, if I move A in this direction, B will move in this direction, and C will move in this direction by the same number of turns, thereby adding a voltage which is in quadrature with the phase voltage of the same amount, and therefore, we will get a voltage here which will be VAN plus delta VAN. Only thing is, now this delta VAN will be in quadrature with this VAN. Similarly, VBN plus delta VBN, which will be again in magnitude same as delta VAN, but will be in quadrature with VBN, and same is the case with phase C, that is delta VCN. This will be in quadrature with VCN. So, if we look at this, this is our AN, BN and CN. I am sorry, this. Now, if we are adding a voltage, this should be at 90 degrees. If we are adding a voltage delta VAN at 90 degrees to this VAN, then now the new voltage is this one. This is the new shifted VAN by this angle. Same thing happens to C, same thing happens to B. So, you will get this phase angle shift for all the three voltage. The change in magnitude is hardly there, but the phase angle has shifted. So, if we have used this transformer on the bus I side, then what has happened is delta I has increased compared to delta J, and therefore, delta I minus delta J has increased, and therefore, increasing the real power flow on the transmission line. Now, how do we model these transformers? Now, basically, if we look at this, what we are trying to say is that we have taps on the transformer which is trying to change the turns ratio of the transformer. Now, turns ratio, when we are talking about, in case of voltage control, the turns ratio, because the voltage is added in phase, the turns ratio is basically a simple scalar quantity. But if we are talking in terms of phase shifting transformers, then the voltage which is added is in quadrature, and therefore, we are talking about complex turns ratios. So, we are thinking in terms of a transformer where the change in turns ratio can be made from the nominal value, which can be in phase or can be in quadrature. That is, we have the taps which can be scalar quantity or which can be complex quantity. Because if we recall our early lesson on per unit system, if we have a nominal, that is, if we have the tap position at the nominal, then the voltage ratio on the two sides is same as the voltage base values, and therefore, the turns ratio is basically 1:1, and therefore, we do not need any transformer as such. But if we are having a turns ratio which is not 1:1, that is, this side the ratio is not same as per the voltage ratio on the two sides of the system, then we have what we call an off nominal turns ratio. And for this kind of a transformer, regulating transformer, the turns ratio will be off nominal whenever the tap position is not at the nominal. Therefore, let us say we have a transformer which has an off nominal turns ratio, that is, it is equal to 1:T. Now, if we have this 1:T, then if we have a voltage VI on this I side, then what will be the voltage at this side? Let us say it is V dash, this will be equal to T times VI, because the turns ratio is 1:T. Now, this Y is basically the admittance of the transformer. It is taking care of the leakage inductance and the resistance of the transformer. So, it is the impedance of the transformer that the admittance of the transformer that we have put here. Now, the voltage here at the terminals of the transformer is Vj, right. Now, we can write down the relationship between Vi and Vj in terms of Y and T. So, let us see how we can do it. Now, the complex power Si is equal to Vi II conjugate, and complex power Sj is equal to Tvi into Ij. That is, if we see here, Tvi is the voltage, and if Ij is the current flowing in this direction, then the complex power entering from this side is Sj, and that is Tvi into Ij. Similarly, the complex power entering from this side can be seen as Si, which is equal to Vi into II conjugate. So, this is what we have written, and II, if we see the directions, then II is equal to minus T conjugate Ij. So, because Si will be minus Sj, because we are considering the transformer to be lossless. Therefore, we can say II is equal to minus T conjugate Ij, that is saying the turns ratio. If the current here is II, then the current here if the current here is Ij, then the current here will be equal to T times T conjugate times Ij, and since the direction of the current is shown as this, and this side it is this, that is II in this direction and Ij in this direction, therefore, that minus sign comes into play. So, II is equal to minus T conjugate Ij. Therefore, the current Ij can be expressed by Ij is equal to how much? Ij will be equal to how much? This is Vj minus Tvi, Vj minus Tvi into Y. So, Vj minus Tvi into Y. This we can write as, this is, I am sorry, here minus should be there. So, this is minus T Y Vi plus Y Vj. This is what we are going to get as Ij. So, multiplying by minus T conjugate and substituting for II, that is for minus T conjugate Ij will yield II is equal to T conjugate into Y into Vi minus T conjugate Y into Vj. So, this is what we will get, that is, we have multiplied the equation by T conjugate, and we are writing minus T conjugate Ij is equal to II, and therefore, we will get II is equal to T conjugate y V I minus T conjugate y V j. Now, T conjugate is nothing but equal to T square. Therefore, rearranging the equations into a Y bus matrix form, we can write the equations as YII into VI plus Yij into Vj is equal to II. In that form, then we will be having T square y minus T conjugate y. So, T square y into Vi minus T conjugate y into Vj is equal to II. This is the equation that we have, T square into y into Vi, T square y into Vi minus T conjugate y minus T conjugate y into Vj is equal to II. And the other equation that we have from here, Ij is equal to T y Vi plus y Vj. So, if we see minus Ty into Vi plus y Vj is equal to Ij. So, in matrix form, we can write the admittance matrix for the regulating transformer in this form, that is voltage current relation for the regulating transformer can be written in this form, which is similar to Y V is equal to I form. If we have only off nominal tap changing, that is voltage control, that is T is a scalar quantity, then from this we can form a nominal we can form a pi equivalent circuit for the regulating transformer, but this is not feasible for the phase shifting transformer where T is a complex quantity. In that case, this will not be possible to do with the physical elements, because you are going to get terms which will require negative resistance and so on. Therefore, we do not form a pi equivalent circuit for the regulating transformers when we are using phase shifting transformers, but we can always include this matrix formulation for the regulating transformer. So, basically, if you see if we have a regulating transformer between bus I and j, then the elements, 4 elements of the Y bus will be replaced by these 4 quantities, that is, this 2 by 2 matrix represents the 4 elements for the Y bus of the system for modeling the regulating transformer. So, let us take an example to see this. We take a 4 bus system as shown here. The line resistance and reactances are given as per this. We have a line from bus 1 to bus 2 with resistance 0.05 and reactance 0.02 per unit and so on. So, we have 5 lines in this system. We have excluded the line charging part in this case to keep the calculations simple, otherwise that can be included. So, now using this R and X values, we can get the admittance for each line, that is, we can find out the Y I j for each line, that will be simply 1 by R plus j x term. So, we can find that out. What we will finally get is the Y bus matrix, which will be a 4 by 4 matrix for this system. So, let us see, if we are calculating, then Y12 is nothing but negative of the admittance of the line between bus 1 and 2. So, this is Y12 minus Y12 and Y12 is 1 by 0.05 plus j 0.2. So, if you see here, this is 0.05 plus j 0.2. So, this is what we will get 1 by this, and the negative sign comes for the off diagonal elements of the y bus. So, minus term is coming here. This comes out to be minus 1.1764 plus j 4.705. You can check these values. Similarly, for y13 we can calculate, this comes out to be minus 1 plus j 3. y14 we can calculate, that is, if you look at this system at this point, sorry, yeah, we have at bus 1 2 lines connected, one to 2 and another to 3. There is no line to 4. So, if we look at this element y12 is given by this, y13 is given by this, y14 there is no line connected. So, it is 0, as we talked in the last lesson, that for a large system we will find that most of the off diagonal elements will be 0, because on an average each bus is connected to around 2 to 3 other buses. So, less than 3 other buses it is connected on an average. Therefore, we will get zeros, like here y14 is 0. Now, what is y11? y11 is basically sum of all y12, y13 and y14 with a negative sign. So, here if we do that, this will be negative of y12, y13, capital Y12, y13 and y14. So, if we add them like this with a negative sign, which is missed here. So, then we will get this as 2 plus 2.1764 minus j 7.705. Same way we can calculate the other elements of the y bus. If you do that, you are going to get a y bus like this. Okay, this is very easy to formulate the y bus of the system. Now, let us see if we replace this line between 1 and 2 by a regulating transformer, then how my y bus gets modified. So, let us replace line 1 2 with a regulating transformer with V by V dash is equal to 1.05. That is, we have 1:t is equal to 1.05. Therefore, t is equal to 1 by 1.05. Okay. Now, we can use the, since we are using scalar value here, V by V dash is equal to this. This is a regulating transformer for voltage control, and therefore, we can use this equivalent pi equivalent circuit for this regulating transformer. So, if we do that, then y v is equal to I relationship for the regulating transformer is given by this relationship, and therefore, the modification in y bus elements will be what? See, we are going to have modification where y11, y12, y21 and y22. These are the 4 elements in the y bus which will get modified, because we are saying that we are having a regulating transformer with a turns ratio of 1.05, that is V by V dash is equal to 1.05, that is 1.05 is to 1. So, if we have this, then 4 elements of the y bus will get modified, that is these 4 elements y11, y12, y21 and y22. These are the 4 elements which will get modified, and we will see how this gets modified. So, this is the value which we should get for the regulating transformer. Now, what we have? We have y11 already calculated for this. Now, if we subtract this y12 from y11, then what we have is basically this line admittance have been removed, and instead of that we are now substituting this value t square y12, where this small y is telling us the admittance of the element, that is the admittance of the transformer. So, instead of the line we have used the transformer. So, we will have this t square into y12 added to that. So, this will be getting subtracted and this will be getting added. So, we will have the new value like this. Similarly, y12 will get modified, that is the old value here, since we have used minus small y12 as this value. So, if we add this y12 to this becomes 0, and instead of that we have to put this value. Now, t conjugate is same as t in this case, because it is a real number, it is not a complex number. So, we have minus t y12. Similarly, y21 will get modified by putting minus t y12. So, add small y12 and subtract minus t y12 from here, y22 does not get modified. If we do this, then what we find is this is the 2 by 2 matrix for the regulating transformer with 1.05:1 as the turns ratio. So, this is what we will get, and so these 4 elements get substituted in the Y bus here, and the final Y bus is computed as this. Now, let us, instead of the voltage control, if we want power flow control, then we use phase angle shifting, and let us say we have V by V dash is equal to 3 degrees. So, here we are not trying to change the magnitude of the voltage, we are only trying to give a phase shift of 3 degrees. So, it is e to the power j 3. Now, this will give again t is equal to 1 by this, which is same as e to the power minus j 3 degrees, right. Now, what we need is, instead of t we substitute this value in the 2 by 2 model of the regulating Y bus model of the regulating transformer. So, here what we will get is again y11 old minus y12 plus t square y12, y12 old plus y12, this makes it 0 minus t conjugate y12. Now, here we are using this t conjugate, t is this. So, its conjugate is going to be plus j 3 0. So, here plus e to the power plus j 3 into y12, and y21 will be again y21 old plus y12. So, this makes it 0 minus t times y12. So, this t is equal to e to the power minus j 3 degrees, and y22 remains same. So, if we do that, we will get y bus 12 as like this, and so these 4 elements of Y bus gets replaced by these elements, then final Y bus comes out to be like this. So, this is how we can take care of the regulating transformer in power system. So, we can have either off nominal turns ratio, or that is the off nominal tap position of the transformers for voltage control, or we have phase shifting transformers. Both can be modeled and as a modification in the existing Y bus, and they can be taken care of in the Y bus itself, and therefore, the other parts of the power flow solution, that is whether you are using Gauss-Seidel method or you are using Newton-Raphson or fast decoupled, you can always use these regulating transformers. Now, what we are showing here, since Gauss-Seidel method is not much in use, we are showing here a comparison of Newton-Raphson load flow and fast decoupled load flow algorithms. We have developed our own load flow algorithms which uses sparse matrix techniques, and all these results are obtained on a P3 machine working with at 800 megahertz. In fact, we have worked it also with P4 machines working at 3 gigahertz. The values will be almost 1/3 or 1/4 of these time that we get. So, for a 5 bus system, the value comes out to be 0.950 milliseconds. It is 950 microseconds basically. Time for Newton-Raphson is around 1.39 or 1.4 millisecond, and so on. 14 bus, it is 1.577 milliseconds and 2.954 milliseconds. So, Newton-Raphson is always taking somewhat more time. Here in fast decoupled load flow, the number of iterations are more. That is, here 5 bus system, it takes around 5 iterations, 14 bus also around 5 iterations, 30 bus it takes around again 5 or 6 iterations, 57 bus it takes around 6 iterations, 118 bus it takes around 8 iterations. Whereas, in case of Newton-Raphson load flow, in all the cases the number of iterations are 4. That is, for the convergence limit of 0.0001, that is after decimal 3 zeros and 1. So, up to that level of per unit in delta P and delta Q, the convergence are obtained for Newton-Raphson in 4 iterations, whereas in case of fast decoupled load flow, it is between 5 to 8 iterations. So, 118 bus IEEE system, it takes around 11.44 milliseconds for the fast decoupled load flow and around 52 milliseconds for the Newton-Raphson load flow. If we do it on a 3 gigahertz P4 machine, this comes out to be around 11 seconds or 14 seconds, I think 11 to 14 seconds, depends on the overheads which are there. So, these load flows, if we are using sparse matrix methods, can be very efficiently programmed, and the time taken is not much. It takes around just 10 to 15 milliseconds for a 100 bus system. Now, we will talk about the applications of power flow studies. Now, power flow, what we are doing in power flow study? Basically, we are trying to find out the steady state operating condition given the loads and the generation at different buses. That is, what we are trying to find is, given the real and reactive power injections at various bus bars, what is the voltage phasors at different bus bars. That is, voltage magnitude and phase angle at different bus bars are computed using the power flow method. Now, once we know these voltage magnitudes and angles at all the bus bars, knowing the admittance of the transmission line or the transmission element, we can very easily calculate the power flow through each transmission element as such. So, real and reactive power flow through each transmission element can be computed once we know the voltage magnitude and phase angle at all the buses. So, power flow analysis provides a steady state operating condition, that is, it provides the power flow, bus voltages, etc. of a power system. So, this is what we get from the power flow analysis. Now, it is a fundamental and most common study in the power for the power transmission network. That is, power flow study is one of the most common study which is done in power system or power system analysis. So, this is in fact, as we will show you, it is an integral part of most system planning and operating studies. All system planning and operating studies depend on load flow analysis. And that is the reason why we have all the time been emphasizing that we need very efficient algorithms for solving power flow for large systems, because we need to do hundreds and thousands of load flow for planning and operating studies. It is a starting point for many other studies. That is, power flow is not on its own just for steady state analysis, but for starting of any other kind of studies, like if you want to do a short circuit analysis to find out what is the current flow in a transmission line, or what is going to be the voltage when a short circuit occurs at a particular point in the system. If we want to do this kind of study, what we need to do is first find out the operating condition before the fault occurred, and then apply the fault and find out how the currents are flowing and what the voltages are. So, first thing that we need to do is to find out the steady state operating condition. And how do we find that out? That is, can be done only by means of a load flow study. So, we need a load flow study for that purpose. Similarly, for transient stability. Now, we are talking about the dynamics of the system. If a fault occurs, how the generator dynamics are going to behave, and all these. If we want to do this study, we do it by using transient stability analysis. Now, this transient stability study also will require as a starting point a power flow study, because we have to start from a steady operating condition and then apply a fault or some outages and see how the system dynamics goes on. So, this is again here we need the power flow study for the initial starting point to start this study. So, it is a starting point for many other studies. Even if we want to do an economic dispatch for the system, then also we need to do this study. We need to know the operating condition, and then only we can think in terms of finding out what should be the generations, and if we get economic generating schedule, again we will need to find out the steady state operating condition to check what is going to be the power flow in each of the transmission lines, what are going to be the voltages, where all these values are within the limits or some limits are violated. So, all these things need to be done, and for all this we need a load flow analysis to be carried out. So, let us see for system planning and design, why do we need power flow? Basically, to evaluate the adequacy of the present and planned system operation. That is, what we are trying to do is, for the present operating conditions with the system lines and generations and loads as it is, we need to find out what is the operating condition, what are going to be the power flows in various lines, what are going to be the voltages at various buses, are these values within the limits, are any transmission line getting overloaded, and so on. If nothing like that is happening, then the things are proper. But if some overloads and other things are there, then we need to take some action. So, we need to evaluate the adequacy of the present system. Again, suppose we are trying to add new generation or build new transmission lines. Now, before we build these, we need to study the system and see that addition of this is going to be having what effect on the system operation, whether these are going to create other lines becoming overloaded, or whether these are going to bring voltages in certain part of the system to a much lower level than what is acceptable. All these things can be studied using the load flow or the power flow studies. Another part which is very important is, when we are doing this planning, what we need to do is perform some kind of a contingency evaluation or contingency analysis. That is, we are planning for a system where if any outage takes place, whether the system is able to take care of the operating conditions without violating any limits. This is because we know that outages can take place at any time. Any line can be hit by a lightning sometime, and that may create a fault, and the line relays or the protection will trip that line. In case this happens, whether the other lines are going to get overloaded or the voltage in some part of the system goes below acceptable limits, all these things need to be checked. So, for this purpose, or if a generator goes out due to some fault, then whether rest of the part of my system generation is able to meet the demand, whether the transmission line which will be carrying now this extra power from the other generators will get overloaded or not. So, all these can be checked up by doing this power flow analysis. So, contingency evaluation, that is any abnormal condition such as generator or a transmission line outage is simulated. So, what you do is in the Y bus you can take that, if suppose we want to take line 1 2 out, outage of 1 2 we are studying, then Y 1 2 is made 0. So, 4 elements of Y bus will get changed, and you can do another load flow analysis. Of course, for contingency evaluation there are other faster methods which are available, which do some kind of an approximate load flow also. So, what happens? This will provide opportunity to the planning engineer to upgrade the existing system. So, that means if we find that due to a load growth or maybe due to our planning we are trying to increase generation in certain part of the system, then we find that some lines are getting overloaded, then we have to plan for upgrading the transmission line in those parts also, so that the overloads do not occur when this new generation comes up. So, this is very useful for studying the system conditions for planning the future. Now, for system operation and control, how we can use this? Again, evaluate the adequacy of the present operating condition, that is the present operating condition, all the flows and voltages are within limits, like this is what all line, any line overloading is there or not, bus voltage violations are there or not, we can check this. Of course, most of the time we will find no such thing for a normal system should be there. But that is not enough, because we cannot say that some outage will not take place. Sometime some outage can always take place, because this is not all equipment cannot work all the time. So, a fault can occur any time on any system. So, what we need to do is whether our system is capable of taking care of such outages or not, and this what we call security evaluation. That is, what we say is n minus 1 security. If n elements are working in a system, then if one element goes out with n minus 1 elements in the system, are we able to run the system without any violation of the operating conditions? That is, no overloading of lines, no voltage limit violations, then we call the system as n minus 1 secure. So, security evaluation in operating in the operational planning, that is for the real time application, we need to do. So, again here what we are doing, the present operating condition may be adequate, but what if any abnormal condition such as generator or a transmission line outage takes place? What is going to happen? Now, in this situation, is the system operating condition adequate for the contingencies, that is for this outage, these outages, is the system operating condition adequate, means without any violation. Now, if you look at this kind of an analysis, then for a large power system with say 1000 buses and 2000 transmission lines, we need to consider outages of each of these 2000 lines taken one at a time. That means you need to do 2000 load flows. That is an enormously complex computation, and therefore, some faster and approximate methods for power flow is generally used for such kind of studies. So, this is all that we are going to talk in this lesson, and in the next lesson we will have a review of the modeling of components and the power flow analysis. So, with this we end this lesson. Thank you very much. Welcome to lesson 23 on power system analysis. In this lesson we will review the topics that we had discussed earlier on power system component modeling. We will start first with the transformer model, then we will talk about the synchronous machine model, and finally we will review the load models. So, since this lesson is basically a review, we will go through the whole thing at a faster pace, because you have already gone through this details of this earlier. So, we will start with the transformer model. As we have said earlier, we have in a system different voltage levels. The generator generates at an optimal voltage level, which is somewhere around 11 to 25 kV. So, generator voltage can be anywhere in between that. We will talk about the model for synchronous machine. Now, synchronous machine have a fixed relationship between the speed and the frequency, and this relationship is given by the frequency f is equal to p by 2 into n by 60. In the next lesson we will review the load flow or the power flow models. Thank you.